In this question, an object of mass m is initially placed at a height nh as shown in the figure A. Object A slides down, passes through a frictional section 1 and collides elastically with another object B, which is of mass 2m and initially at rest on the horizontal surface. After the collision, as in the figure B, object A moves back through frictional section 1 and eventually comes to rest at height h, capital H. Object B moves through another frictional section 2, finally comes at rest at a height of 7h by 2. The energy lost by A during each pass through section 1 is equal to the energy lost by B while passing through section 2. No energy is lost during collision. Motion is confined to a same vertical plane, and any other forms of friction aside those in section 1 and section 2 are neglected. So the question is, determine the final height capital H to which the object A rises after passing through section 1 for the second time. So these are the two figures. This is our figure A and this is our figure B. Object A is placed at a height of nh and it slides down and passes through the frictional section 1. So this is the only frictional part. Entire is frictionless. So this is called as a section 1. Section 1. Similarly, this is B, which is initially at rest, and for B, this is our section 2, which only have the friction part. Section 2. Similarly, this is our section 1 and this is our section 2. 1 and 2. So after collision, A moves back the inclined plane and comes to at a rest at a height h, capital H, and B moves further up the inclined plane and comes at rest at a height 7 2 by h. So we have to find out what will be this value of capital H. And so mass of A is given as m, mass of B is given as 2m. Initially, this block B is at rest and A is traveling below the inclined plane from the height of 9h. So first we are going to start with our conservation of energy as well as momentum, because in the question it is mentioned that there is no energy lost in the collision and the friction beside this section 1 and section 2 can be neglected. Okay. So let us say that our velocity of A just before the collision is given as v. Velocity of A just before collision is, let us suppose, given as v. Velocity of A just before collision is v, and just after collision is va. Just after collision is va, and the velocity for B before collision is 0 because it is rest. So we say velocity of B just before collision will be 0 because it is rest, and just after collision is VB. just after collision is Vb. So Va will be having a velocity of V just before collision, and B is having a velocity 0, and after the collision A will be having a velocity of Va, and B is going to have a velocity of Vb. So we can use the conservation of energy as well as conservation of momentum. So we can say conservation of energy and for the conservation of energy we are only going to consider this portion. Similarly, for the conservation momentum we are also going to consider initial, and this will be our final. Only this portion, neglecting the section 1 and section 2, okay, because the friction is there in section 1 and section 2 only. So conservation of energy before collision will be equal to energy after collision. And please keep in mind that within this area, this one, the only energies are present are the kinetic energy. There is no as such potential energy. Potential energy is beyond the section 1, so there is some friction loss here. Similarly, after collision, immediately after collision, the energies will be within this area. Okay, and we can write that before collision we are going to have half m v square plus 0 will be equal to half m va square plus half 2m vb square, and this half cancel throughout and m also goes away. So we can write that our v square will be equal to va square plus twice vb square. So this is one of our equation. Now we are going to use conservation of momentum. Conservation of momentum. Initial momentum will be called final momentum. Initial momentum is equal to final momentum. Initial momentum will be equal to mass into velocity, and this is for A, plus 0 is equal to mass for, this is for A, and we get this as for B, and mass cancels out throughout, so we get the equation that V is equal to VA plus twice VB, and this is our equation number 2. Now if we solve equation 1 and 2, we will be able to find the value of VA and VB with respect to the velocity V. So equation 1 was our in V square, so using equation 2 in equation 1, using equation 2 in equation 1, we get VA plus twice VB whole square will be equal to VA square plus twice VB square, and this gives us that VA square plus 4 VB square and plus 4 VA VB will be equal to VA square plus twice VB square, and VA cancel out. Here we have 2 VB square and 4 BB square, so we can write this as 4 minus 2 will be equal to 4 minus 2 multiplied by VB square will be equal to, and here we get this as minus 4A 4B. This gives us twice VB square is equal to 4 VA times VB. Twice goes with this and square with this part because we are interested in one value. So therefore we can write, here it will be minus VB is equal to minus of twice VA. Now we got the relationship between V and VB. Therefore we can write that our V, which was equal to VA plus VB, we substitute, we get VA, and this is minus of twice VB, missed it, minus of 4 times VA. So this gives us that V is equal to minus 3 VA, or we can say our VA is equal to minus 1 by 3. V is equal to minus 1 by 3 of VA, and if we use this equation from here, we can say that our VB will be equal to minus is plus 2 by 3 times, one second, yeah, I made a mistake, this is to be VA and this is to be V, and we get this as times our V. So from here we got that our VA is minus 1 by 3 times V and VB is plus 2 by 3 by V. So we can find out now respectively the kinetic energy of block A just before collision, or we can say after collision rather. We can say kinetic energy of block A after, one second, let me rephrase it. I can say after collision kinetic energy for A, let us call it as kinetic energy of A after, this will be equal to half m VA square, and VA we already know in terms of V, we substitute here, we get half m, and this comes 1 by 3 minus times V and whole square. So let me write this A only, we will see that later on. And therefore we get that kinetic energy of A after collision is equal to 1 by 2 mv square times 1 by 9. Similarly, we can say for B, kinetic energy of B after collision will be equal to 1 by 2, mass is 2m, and we have Vb square. We substitute the value, we get 2 multiplied by 2m, and this is our 2 by 3v whole square. So we get kinetic energy of B after collision will be equal to half mv square multiplied by this comes as 8 by 9. So we find out the ratio of kinetic energy of A after collision divided by kinetic energy of B after collision, and this will be equal to half mv square 1 by 9 divided by half mv square, and we have here 8 by 9, and this ratio, or this comes as 1 by 8. So we can say that kinetic energy of A ratio kinetic energy of B is 1:8. Now we assume that the kinetic energy of A after collision is suppose E. We say let kinetic energy of A after collision is represented as E because it is 1 only ratio wise. Therefore, we can write that our kinetic energy of B after collision will be kinetic energy of B after collision can be written as 8 multiplied by E. Once again, we can use conservation of energy principle, which states that conservation of energy, which means energy after collision and energy before collision will be equal. Therefore, we can say that energy before collision will be equal to energy after collision, and before collision energy will be only associated with block A because block B is stationary. Okay, so we can write this as that kinetic energy of B, so we can write kinetic energy of A plus kinetic energy of B, and this is before collision will be equal to kinetic energy of A plus kinetic energy of B after collision. And B is our 0, so this goes away. So we get that kinetic energy of A before collision, before collision will be equal to kinetic energy of A we just calculated is our E, and for B is our 8E, and this comes equal to as 9E. So it means kinetic energy of A just before collision. Okay, please keep in mind this is just before and this is just after. Now we are going to consider the movement of the various blocks, block A as well as block B. So let us first of all start with for block A. And block A, initially it is traveling down the inclined plane to the horizontal surface. So initially, so this is our horizontal surface. block A is somewhere here, and the height from which it is going to slide is given as 9 times h. This is our section 1, which is the frictional part. Let us suppose, and block is traveling in this direction and it reaches somewhere here before collision. And we say that this is our section 1 that consists of the friction part. This is our section 1. Obviously there will be some loss here. Let us call that loss as loss of because of A. And we assume that this loss of A is equal to our E naught. And this is, please keep in mind, this is before collision, it is moving in the downward direction. So for block A, before collision, for this figure, before collision, we can say that the potential energy at height 9h, and there is some loss of energy, and there will be the final energy, which we have just found out is our 9e. Okay, so let me write it here. We can say that our the energy at, let us call this as point P, and this is point Q. So we can say that our energy at point P minus loss because of this frictional part will be equal to energy at point Q. And energy at point P will be our potential energy. So we can write this as mg 9 times h minus loss we assumed is given as E naught. So we write this as E naught will be equal to energy at Q, and energy at Q, that is just before collision, we found out is equal to 9 times E. So we can just remodify this equation is 9 mgh minus E naught is equal to 9 times E. Let us call this as equation number, I think this should be 3 or something like that. Yeah, this is equation number 3. Now we come to block A after collision. Okay, so this was our before collision. Now we come to after collision. So after collision, block A will be moving up the inclined plane. So this is our block A. We have a frictional part which we call that section 1, and it is moving up the inclined plane, and now the block is somewhere here, and the height is for this block is given as h. And if for section 1 we just assume that this is given as E naught. Therefore it is moving up the inclined plane, so energy at this is still our point Q, yeah, and let us suppose this is Q and this is point R. Q and this is point R. Let's remove this, let us call this S, much more convenient because this is after collision. Okay, so we can write the equation that energy at S minus the loss of section energy, which is our E naught, will be equal to energy at R. And energy of A after collision, this is block A, is our E. So we can write this as equation E minus E naught will be equal to energy at R will be our potential energy, that is our mg capital H. Let us call this as equation number 4. Yeah, just after collision it is E, and after, you can say, sorry, I missed something. Yeah, here it is. Energy of A, kinetic energy of A after collision is just E, and we have used, yeah, just after collision it is E. It's correct one. And this is our equation number 4. Similarly, we are going to make the analysis for block B now. We say for block B, and block B will be having only one motion, that is up the inclined plane, because initially it was at rest. So this is our block B, and this is the frictional section, that is section number 2, and block B is moving up the inclined plane, and it will be somewhere here, and its height, that it is given as 7/2 times h. And it is also mentioned that the loss of section 1 for block A will be equal to loss of section 2. So it means this frictional loss will be once again is equal to E naught. So we can write now equation that for block B after collision. After collision, so let us call this as point T and this point as Z. Okay. So we can say that energy at T minus E naught will be equal to energy at Z, and energy at T is the kinetic energy which is associated with B, and that is after collision, which is our 8E. So we write this as 8E minus E naught will be equal to the energy at Z will be our potential energy, which will be equal to 2mg multiplied by 7/2 h. So here 2 and 2 cancels out. So we can write this as our, we can write this as 8E minus E naught will be equal to 7mgh. We got almost all the equations. This is equation number 5. Now it is simple addressing the solution of these equations. Okay. So from equation 1, sorry, not equation 1, but equation 3. So we can say from equation 3, we get that our 9E plus E naught is equal to 9mgh, and we have equation 4, which is our, one second, I missed one equation. Equation 3 is our 9E plus E naught. Yeah, this is the correct one. And next is our, yeah, equation 5. So equation 5, let me write it here. Equation 5 is our 8E minus E naught is equal to 7mgh. So if we divide them, mgh cancels out, and this comes as 9/7, and we solve it. we can write this will be coming as 72 times E plus 7 times E naught is equal to 63 times E, and we have this as minus 9 times E naught. One second. This is our 63 and this we have here 72. Yeah, this is correct now. So this gives us 63 minus 72 times E is equal to minus 9 minus 7 times E naught. So we get this as minus 9E is equal to minus 16 times E naught. Minus goes with minus. So from here I can say my E naught is equal to 9 upon 16 times E. So we got the relationship between the loss in section 1 and 2, 1 or 2 rather, and the total potential energy or total energy that is associated with block A after collision. Now we already know the equation that our E minus E naught is equal to mgh. We know that our 9E plus E naught is equal to 9 mgh, and we also know that E minus E naught is equal to mgh. So if we divide them, mg and mg cancels out and this comes as 9h divided by capital H, and E naught we already know. We substitute the E naught in this equation, we get this as 9E plus we have this as 9 upon 16 times E divided by E minus, and this is about 9 upon 16 times E is equal to 9h divided by capital H. Here E cancel out and here 9 cancel out throughout. So this gives us 1 plus 1 upon 16 divided by 1 minus 9 upon 16. This 9 cancels with this 9 and this is our H upon capital H. Now if we take LCM, we get this as 16 plus 1 divided by 16 minus 9, and 16 cancel with 16. So this comes as H upon capital H. This is our 17 divided by 7 is equal to H upon capital H, and we have solved it. We get capital H is equal to 7 upon 17 times small h. So this was supposed to our final answer, that this is the height to which block A rises after collision. So this question was quite interesting. Only thing we have to remember, the place where we have to use the conservation of energy. That's the most important part here. Rest was simple calculations. So this completes the question. Thank you.